So a determinant of a matrix exists in square matrices, and we can actually use a couple of little tricks to find those determinants. They do have uses inside of them. We'll discover in just a moment that you can use the determinant to help you discover the inverse of a matrix. And we'll also discover there's some other little clever tricks that you can use determinants for. Majority of those you will see in linear algebra if you end up taking that course as you go on through your math. But let's just go ahead and jump right into the determinant for a 2 by 2 matrix. And it turns out you've actually already seen how to do the determinant of a 2 by 2 matrix. If you've learned how to do the inverse of a matrix, you'll remember there's a formula that says 1 over A times D minus B times C times a modified matrix where you have D, A, minus B, and minus C. This is to find the inverse of A, provided that A is a matrix little a, b, c, and d. So at the very beginning I said that the determinant can help you find the inverse, and that's actually because this right here is your equation for the inverse of a 2 by 2 matrix. So a lot of people end up trying to memorize this, which it's not that hard. It's only about 4 letters. It's a very, very simple equation. But in order to help you out with a 3 by 3, what I suggest doing to remember this equation is to say it is the left to right diagonal. So negative 3 times 1 minus the right to left diagonal. So 4 times negative 2. And that's how I remember it, because we're going to see in a minute a 3 by 3 matrix ends up dealing with a lot more numbers, and there is an equation for it, but it would get very, very nasty, and there's a lot of memory involved in that. And to be honest, I don't have that good of a memory, so I just assume my students don't either. But if you want to look up an equation for it, you're more than welcome to, or you can figure out your own by substituting A's, B's, and C's instead of numbers on the 3 by 3. But let's go ahead and finish up this 2 by 2. The left to right diagonal is negative 3 times 1 minus the right to left diagonal is 4 times negative 2, giving me a negative 3 plus 8, which gives me a final answer of 5. So that would be the determinant of this matrix right here. Not too bad on 2 by 2 matrices. So let's go ahead and jump to a 3 by 3. So a 3 by 3 matrix, there is a little trick to it. There's an official way of solving it using another method, but this is the method that I enjoy using. There are plenty of other videos out there teaching you other ways to find determinants of 3 by 3 matrices. One thing to note real quick is as you're looking through and finding the determinant of a matrix, you may actually see it written a couple of different ways. If we call this matrix B, since we've already talked about a few other matrices. Ooh, my board's running out of battery, sorry. Matrix B, there we go. If I wanted to know what the determinant of matrix B was, I might write it as determinant of B, or I might write it as det B if I'm feeling a little bit lazy, or I might write it as what looks like absolute value of B. It's very, very important that when these absolute value signs are around matrices, you're not simply changing all the negatives to positives. It doesn't mean that type of thing. And also when you're doing absolute value of regular numbers, you're not just changing it to positive, it actually means something. But that's a side thing for another. This is all the different ways that I could ask for the determinant of B. So let's go ahead and find the determinant of B. What I do is a little trick. I'm going to copy down the exact same matrix, negative 1, 3, 7, and 2, negative 2, 0. And I'm going to take these first 2 columns and I'm going to tack them on at the end. So I'm going to recopy 5, 4, 1, negative 1, 3, 7. So again, I just took these first 2 columns and I copied them on over here to this side. Just copied them straight on over. And the reason that's useful, and also the reason that I told you to remember left to right minus right to left, is because that's the same procedure for a 3 by 3. Now the only difference is we're dealing with full diagonals. I don't care about this singular one by itself. I don't care about the 4 and 7. I care about any diagonal that has 3 entries to it. So 5, times 3 times 0. And then there's another full diagonal, -1 times 2 times 1. So I'm going to add that. -1 times -2 times 1. And then I see another diagonal here. So I'm going to add that. 2 times 4 times 7. So I've finished all of the left to right diagonals. Now I need to worry about the right to left diagonals. So again, I only care about full diagonals. So I'm going to subtract all of the right to lefts. -1 times 4 times 0. I see another one, so I'm going to go ahead and subtract that as well. -5 times -2 times 7. And I see one more diagonal here. So I'm going to subtract that one as well. 2 times 3 times 1. So now I've got this big long equation, and all I have to do is just start solving for these things. So I see 5 times 3 times 0. Well, since there's a 0 in there, that's just copied right on down. -1 times -2 times 1 is going to give you just a positive 2. Plus, and then 2 times 4 times 7 is going to give you 56. Now we're moving on over here. -1 times 4 times 0, since there's a 0 in there. And then we've got 5 times -2 times 7 is going to give you a -70. And over here we have a 2 times 3 times 1 giving you a 6. This is something I would feel comfortable punching into my calculator or figuring out in my head. Regardless of what method you use, don't forget to be very, very careful with those minus negative signs. So if you guys are going to be doing this in your head, you have to be real careful around this part. And if you're doing it in a calculator, make sure you're real careful about doing that. But when you plug all this in together, you'll end up with 122 as your determinant. So again, as a quick review of what we did to find this determinant is we took those first two columns and we tacked them on at the end. We did all of the left to right diagonals minus all of the right to left diagonals. You can figure out an equation for it if you wanted to by substituting in A, B, C, D, E, F, G, H, I, and then you'll get some big old thing here. But again, I strongly discourage people from trying to memorize equations, especially ones that are long and complicated like that, when you can discover them and you can figure out a pattern. Patterns are very, very, very important to math, and they end up discovering a lot of things that create equations that you couldn't normally come up with. So let's go ahead and do one more thing with this. One of the important things that you can do with the determinant, as we discussed on this slide, is you can use the determinant to find the inverse, but you can actually use it as well to find area of triangle. So the area of a triangle, we've discovered a lot of different ways to find that area of a triangle, but we can actually do it if we know the location of the vertices. So if we have a triangle that's located at x1, y1, that's one of the vertices, another vertex located at x2, y2, and a final vertex at x3, y3. What we can actually do is take these 3 points and put them into a matrix. So if I put it into a matrix that is x1, y1, and then the number 1, and then x2, y2, and then another number 1, and finally x3, y3, and another 1. If I create a matrix from all of those points, let's call that matrix P, we can use this matrix to figure out if we have, what the area of a triangle is. So the area of whatever triangle we're looking at is going to be 1/2 times the determinant of P. Remember, the determinant is those absolute value signs around P. Now we run into a problem though, because depending on how you organize these, you may end up with a negative determinant. And if you end up with a negative determinant, you have to change it to positive. So what we do is we put absolute value signs around the outside. So I know that this is confusing because you've got two sets of absolute values. This one tells you to find the determinant, and this one tells you to take the absolute value of the answer that comes out. So it seems very complicated at first look, but let's go ahead and put it into practice and find the area of this triangle right here. So I'm going to go ahead and take these points, And notice it doesn't matter what order I take these points. If I decide to say that this one's P1, this one's P2, and this one's P3, I'll get the exact same answer as if I do it in P1, 2, and 3. So I'm going to go ahead and do it in that little funky order, and if you don't believe me, go ahead and do it in the regular order of P1, P2, P3. We'll end up with the exact same answer. So I'm going to create my matrix P here, and again it's x1, and then y1, and then the number 1, x2, y2, and the number 1, last but not least, x3, y3, and the number 1. So I know to plug into my equation, the area of a triangle is equal to the absolute value of 1/2 times the determinant of P. I need to figure out the determinant of P. So I'm going to go ahead and do that by following the same method we did on the previous section. I'm going to copy down my matrix, and then I'm going to take these first two columns and tack them on at the end. So 5, -4, 3, 0, 2, -2. Excuse me, that looks like a Z. -2. And again, left to right minus right to left. So I've got 3 diagonals here. 5 times 2 times 1 plus 0 times 1 times 3. And last but not least, 1, -4, -2. So there are all my left to right diagonals. I'm going to subtract all of the right to left diagonals. So 0 times -4 times 1 minus 5, 1, -2, 5, 1, -2 minus 1, 2, 3. 2 and 3. And at this point, it's just number crunching down there. We've got, excuse me, forgot to change colors. 10 plus 0, 1 times -4 times -2 is going to give me a positive 8. We've got a 0 here, minus -10, and then minus 6. So figuring all this out, we've got the 10 and then the 8. Again, be careful with the minus a -10. Will give us a value of 22. So this is the determinant of P, which means I just need to plug that into my equation. Area of a triangle is equal to the absolute value of 1/2 times 22, which gives me an area of 11. So again, depending on how you organize these, rearranging them, if you had decided to do P1, P2, P3, you may have ended up with a negative determinant. That's why those absolute values are so important. The very last thing that could happen is there is a chance that this number would turn out to be 0. So if your determinant of this ends up being 0, then that means that the area of your triangle is 0. So let's think for a moment, how can the area of a triangle be 0? So let me put a little bit grid space here. And what I'm going to do is I'm going to put some dots on here. And in order to make a triangle, you have to have 3 points. So the area of this triangle doesn't equal 0. It doesn't make sense. Let's throw up a couple more dots. Let's see a triangle here. That doesn't have an area of 0. So I throw dots on here, try and mentally create a triangle that has an area of 0. And as you look through here, every single dot combination that you come up with will form a triangle. But if you look carefully, if you take this as one of the vertices, this as one of the vertices, and this as one of the vertices, you don't have a triangle. You have 3 points that are what's called collinear. So let me go ahead and get rid of this background. It's starting to hurt my eyes a little bit. These 3 dots are what are called collinear. So if you end up with a determinant, so if the determinant of P equals 0, then your points are collinear. And that's a very important fact that can help you guys out with complicated math problems in the future. So again, determinants, I like to think of them as left to right minus right to left. With 3x3s, it's a little bit more complicated, but practice, practice, practice. That'll get you what you need.